You should click on the table again. You should click on the presentation again so that I can switch the pages. Okay, it's working. Welcome to my presentation. First of all, let me present myself. I got my bachelor's degree from Bilkent University this semester, and now I am starting my master in Bilkent again. And my mentor was Feride, Ceren, and Kose. I'm thankful for her giving to me a lot and discussing me with these topics. Let's start. Here's my summary of the talk. We will first start with defining, not defining, giving an intuition to understand the concern of algebraic topology. Then for that purpose, we will define the fundamental group. And to get the Van Kampen theorem, we also need categories and limits and colimits to be defined. And at the end, without giving the proof, I will show you two examples. Okay, what's algebraic topology? On one side, we have algebra. In general, we have a set and a binary operation and various properties. According to which properties are satisfied, we will have a different algebraic structure, right? A groupoid or a monoid, a group, sorry, not groupoid, a monoid, a semigroup, a group, field, ring, etc. And on the other side, we have topology. We have topological spaces, a geometric object. And in topology, we have continuous deformations. But be careful, while having a continuous deformation, you shouldn't close a hole or open a new hole, tear it, glue it, or passing through itself. So you are allowed to do these moves. Now, algebra will be our tool to understand topology. And at the end of the day, we will have a classification of topological spaces using the tools of abstract algebra. So what we will need is that we will have an algebraic structure in topological spaces so that it has some invariance. It has some invariance under continuous deformations. Okay, let's start defining the fundamental group. Let me first of all say what pet homotopy is. Let X be a topological space and XY in X. We say two paths are homotopic. Let's say this is F and this is G. We say they are homotopic if we deform the F continuously to the G. And all of the paths have the same end and starting points. Now, we want an algebraic structure to be defined on topological space, but we cannot define an algebraic structure on these paths. Why? Because we cannot put them into a binary relation or operation, right? How can you put an operation between two different paths which have different endpoints and starting points? So that's why we are identifying these points and at the end getting a loop. And now we can define the algebraic structure that fix a point and having a loop around that point. Be careful. We are defining the group to be the set of equivalence classes because what we want is to have an algebraic structure that is invariant under homotopy. So homotopic loops will be the same in the same equivalence class. Then, when we fix a base, we will have a group on this topological space with the identity element that is constant map, and that is the constant loop, and the inverse of an element will be given as traversing the loop on the other way around. It's also easy to check that the composition passes through the equivalence classes. These are some daily life examples. We want to distinguish them in algebra. These are basic examples. Let's say we fix a point 0 on real line, then any loop that is starting at and ending at 0 can be shrinked into 0, right? So our group will be trivial. Again, in S1, the unit interval, we will have let's say we pick the point 1, then we have two choices. You either go around clockwise or counterclockwise. That will be the clock. Let's say clockwise is +1 and counterclockwise is -1. And it is again trivial if n is greater than 1. We will need categories since we have on one side algebra and on the other side topology. These are categories that I will give more examples, but we have a categorical language to express these transformation between those categories. Okay, as we said, algebraic topology concerns mappings from algebra to topology, topology to algebra, and category theory provides us with a language to express these mappings. Okay, what's a category? A category C consists of objects. We need objects and morphisms between any two objects, and identity for each object, identity morphism. We also need the composition law. Let's say you have two groups and three groups. You have morphism from one to another and morphism from one to the last one. Then the composition will be another group homomorphism, right? Okay, and it must be associative. Okay, we can also pass through the categories. That's a map called functor. A functor from C to D is a map of categories where it assigns each object of the first one to another object of the second. And it must take the identity morphism of this category to the identity morphism of its image. Okay, and the composition distributes over the functor or all morphisms. These are the examples, a few examples here. You can think of a set, category set. Objects are the sets and the functions. An important example here is the vector spaces over the field K, where the morphisms are the K-linear maps. And our concern is here, top star, which is pointed topological spaces, base preserving continuous math, the homomorphisms. Okay, let me define what a limit and colimit is. Before that, let me tell you what the diagram is. What a diagram is. A diagram is the image of the first category under a functor in the other category. Okay, its image basically under factor. From now on, okay, we have a functor from I to C. Let's say this is an indexing category, and we are taking its morphisms to the here, and let's say A to B is our diagram. The limit will have two basic properties. One is the universal property that for any other object in the category with morphisms, any morphisms that we can write to the diagram, then we should have a unique morphism from the other object that is in our category to our limit. And all of these triangles are commutative. The definition of the limit is similar. Just you change the rotation of the arrows. Now you are going a cone over the diagram. Okay, here's an example of a limit. In this case, we have a diagram like this. Like let's say we had a puncture, and in our category we have such a diagram. I'm not saying this is f of blah blah in this category. Just think of it as the primitive object we have. Then we are trying to find the limit. The limit in this case called pullback, if it exists. And because this h can be given by these two arrows, since it's commutative, okay, we can omit this and say this is the limit. And in the category of set, it is given by this because you have to. This is pullback, okay? We have a point from x and a point from y, but at the end, since this is commutative, f of x must be equal to g of y, so it will be a subset of the product of sets. And here's another example of push out. We call it. In this case, the diagrams has arrows. Arrows in another direction. So no problem. And Again, this h can be given by the long sides of the square. And in the category of topology, the colimit will be equal to the product of the disjoint union of the spaces. It's quotient by the since Z should be mapped to the same place, they will be identified. Okay, let me give you the, now we can give the Van Kampen theorem. I will give an easy basic form of version of it. We will have two subspaces of our topological space. They are U and V, where they are not empty and the intersection is not empty. Also, they are open and path connected. Then the fundamental group of X will be isomorphic to the free product of the first, sorry, this should be U. This should have been U. The first, the fundamental group of U, free product with fundamental group of V, but it's an amalgamated product. We have the generators of this group and generators of this one, but the intersection will be will have the same elements. So we will contribute its relation to the free product for any base point. So our base point should be in the intersection. Now we can have two examples. How much time do I have? Okay. Let's start by computing the fundamental group of torus. This is called the fundamental polygon of torus, since you can have a paper and glue it on the sides. Then you will get a sphere without its heads. Then connect the heads on the same orientation over heads. Then you'll get the torus. Sorry, here it is. It's not visible there. Okay, you'll get torus. Now, remember, let me tell you first this. Notice that here, this is the colimit of the diagram, where I will tell you. That's why I told you the definition of colimit. Let's say we have two sets on. We will do the computations on this polygon. These sides are identified, A and A. Here is B and B. What we need, we need two open sets. Covers X. Let's say this is U. And this side is V. Let's say they have an intersection like this. I need another color. I have time, right? Let's say this is U. And this is V. Then they have an intersection here, U intersection V. And take a point here, X. We have such a diagram where we have a topological space and it has subsets, right? U intersection V is included in U, and U intersection V is included in V. So our morphism in our category, the inclusion map. And we are looking for the colimit of this diagram, where we said the colimit here is the amalgamated product of these two spaces with respect to the relation in the intersection. What we have here, this is a unit disk inside the, say this is U and this is V. Let's see, U is a unit disk, so its fundamental group is trivial. You can shrink it to a point, to this point. So its fundamental group will be 1. And now focus on this area. You can shrink it to the boundaries of this polygon here, and note that we should get their image in the same in the fundamental group of X. So we have a generator A, B, because of the V here, and the relation I have no more space. Shrink it to the stretch it to the boundaries, then 1 will be equal to A, B inverse, A inverse, B. This is the relation. Okay, we have computed the fundamental group of torus. Now, do I still have time? Yes. Let us compute the fundamental group of Klein Bottle as well. First, you get a Mobius chip. Then you identify these lines as well on the same orientation. But note that as in torus, we are not going to have the perfect match on the orientations. Why? Because we are starting with the Mobius shades, and at that point, you got let's say you have a cylinder without its head, but the orientation is not the same. It's the other way around. So you got to put it inside the other. We got, where is the picture? Here is the picture. The idea is just the same. Just the same. You draw U here, V here, we have A's, B's here. Now again, the fundamental group of a disk is 1. We have generators A and B inside B, and a relation as follows. Again, the idea is the same. You stretch it to the boundaries. Here we get 1, so 1 will be equal to, in the intersection, A, B inverse, A, B. Can you see? Okay. This is the end. You can do more examples like computing the fundamental group of a sphere, or yeah, you can compute the fundamental group of the sphere by the same exact idea. Thank you for listening to me. This is the end. These are my references, and thank you. I wonder how much you understand from my presentation. 100%.